Hello, everyone. This is just a quick introduction because I forgot to record an introduction during my conversation with Professor Beghi. This is the first time that I have recorded a podcast and is quite interesting. I think I was quite awkward during the conversation, but it's okay. It was also Professor Beghi's first time recording an interview. So, yeah, it was quite fun. But I decided to record this interview because, of course, learning quantum mechanics is quite hard, but I feel like teaching it is even harder because you deal with people from different backgrounds with different questions, and you need to make to kind of adapt to it. And Professor Beghi is kind of a specialist on that because teaching in Politecnico di Milano for a long time, he deals with so many students from all over the world, and yeah, he had to adapt a lot throughout the years. And nowadays, he has quite an interesting course that we're going to discuss during the podcast. We also discussed a little bit about his background and how it is to be a professor and a researcher in Italy is a different experience from Brazil or maybe from other countries. I'm from Brazil, so well, it's quite different here. Also, the oral exams, which is the way that we're going to be tested here in Polytechnical, especially on his course. And yeah, I haven't had an experience before with oral exams, so I was curious to know and to learn a little bit more from him was how he intends to test us during the oral exams. Recently, I just had my oral exam, so I'm gonna do a whole lot of video discussing more specifically how was the experience in Politecnico di Milano with the courses, and I will talk about the oral exam. It was quite a fun experience. But yeah, this conversation in general will be about the challenges of teaching quantum mechanics, and I hope you guys enjoy it. It's a little bit long maybe, but I had fun recording it, and I ended up liking Professor Beghi very much. He even took me for a coffee, and yeah, he's a very kind person, and I really enjoyed the conversation, to be honest, and I hope you guys enjoy as well. So yeah, see you in a bit. I'm here with my professor, Professor Beghi. He teaches quantum physics for me here in Politecnico di Milano, and today he accepted to talk to us about his experience here in being a professor in Italy, like his trajectory as both as a student and as a researcher, and now as a professor. And he agreed to talk a little bit with us. And he's very he helps the students, and he's very excited about teaching, and that's why I invited him to talk a little bit with us.
So thank you for inviting me. And, yes, I am. This is quite being interviewed like this is quite a new experience for me. So let us try.
Okay. Well, I invited him to. We're going to talk about the challenges of teaching quantum physics. This is the main goal of the video, but in the beginning we're going to start discussing Professor Beghi's career and his experience as a student, because his background is from engineering, but nowadays he's a physicist, let's say. And then but let's start discussing that. Like, Professor, how did you get into this, right? We were discussing before.
Yes, I mean, when ending high school and wondering which university I would take, I was quite uncertain between engineering and physics. And then I ended up, because in nuclear engineering curriculum in Politecnico comes from the merge of different origins, and there was a strong root in physics. And so there was a possibility to adjust the study plan more on the plant point of view, so fluid dynamics and mechanics. But there was a possibility of tuning the study plan more on physics, and this was interesting, and this is what I did. And then my physics supervisor was a physicist, and so following him, I entered university in a group of matter, which is essentially physics. So I knew since the beginning that my possibility of teaching was essentially in physics, and I did like it.
Mm-hmm.
So
Awesome.
this is I started. I mean, my physics supervisor was teaching solid-state physics for many years. I did for his course the practical exercises,
Mm-hmm.
and then I began to have my own courses. First on what here is called Physics 2, which means essentially for electromagnetism and optics.
Mm-hmm.
And then the course of Introduction to Quantum Physics, which also adds different variants, and also other courses in physics.
That's great, Professor. Thank you. Also, we were discussing a little bit about the differences in the educational systems. Like here in Italy, you were discussing before with us, like we were taking a coffee. We were discussing about that, like the trajectory, because high school here in Italy is 5 years, and then the bachelor's have a different duration, in general like 3 years, right? And then the master's is 2 years, and then PhD. So it's quite different from the experience in Brazil, and I feel like in also other countries. And then I would like you to discuss a little bit about that, like your trajectory, like going from, like, because Professor Beghi, he's very oriented to teaching. Like he tries as much as possible to make concepts that are complicated clear, and then but of course there's the challenges of dealing with like teaching well and also the research, because university requires both. I would like you to discuss both this part, like first like this trajectory, how the education system works, and then like about like teaching versus research here in Italy for a professor.
Yes. Well, let me just make some recollection. I mean, which by now have essentially a historical perspective.
Mm-hmm.
I mean, back in 20th century, the Italian system had a high school of 5 years, which still it has,
Mm-hmm.
and most university there was not a distinction between bachelor and master.
Mm-hmm.
It was a single course, which depending on the topics was 4 or 5 years, and without an intermediate step. So at that time, and there were no formal graduate studies. So at that time, once one reached the laurea at the end of 4 or 5 years of university, and after 5 years of high school, the level was more similar to that of a master's degree than to that of a bachelor. Then in 1980, formal graduate courses were introduced. Before that, there was no PhD title issued in Italy.
Mm-hmm.
And then even later on, it was really at the end of 20th century, the courses of 4 or 5 years were split into a 3-year bachelor and then a couple of years of master.
Okay.
And then there was the doctoral possibility. So the system that deep in 20th century was quite different from that of our countries, gradually evolved to become more similar to that, in particular of Anglo-Saxon systems. Also because, you know, in the last century, cultural exchanges were not so strong. Any country had its own trajectory, and then exchanges became more and more easy and frequent. And so the need for a certain uniformity or possibility of comparing curricula became more evident, and so the trajectory evolved to something more similar. Nowadays the bachelor, master and doctoral sequence is quite widespread, and it is also, I mean, since the end of 20th century, it is also completely formally established also in Italy. When you were asking me about teaching and research, I mean, are both my interest.
Okay.
And I am basically an experimentalist. I'm not a theoretical physicist. And at the beginning of my career, I worked more. Basically, I've always been on physics of materials. In the first 10 years of my career, I was more on mechanical properties and physics of dislocations and measurements about the plastic, the deformation of metals. Then with my colleagues, we switched to a more physically oriented topic, and this became as Brillouin spectroscopy. And Brillouin spectroscopy is, one could say in a synthetic way, is an optical way of measuring acoustics. And this is interesting for thin films. This provides interesting insights into the behavior of thin films.
Okay.
And this has never been so strictly linked to my teaching. I taught this course on electromagnetism, and then courses on introduction to quantum physics, because this is what the faculty needed, what the curricula needed, and I found it interesting because digging into the roots of topics, you always find something interesting.
Okay. But then, how did you start, in quantum physics? Of course, you had it in your courses in graduation and in masters, but how did you start, your trajectory in quantum physics? It was self-study, or you had professors who helped you, in your early years, and then after, of course, you became a professor as well?
Well, in my education, I had a formal course on quantum physics, a course on atomic physics, a course on solid-state physics. So there was quite a background. Then I helped, my physics supervisor and also another professor who were teaching. One was teaching solid-state physics and the other one was teaching atomic physics. So for several years I did the exercise parts of these courses.
Yes.
So I had the opportunity of deepening my knowledge. And then I felt ready to have my own course on quantum mechanics. It has always been an introductory course, basically aimed at students who had not been previously exposed to it.
Yes.
And first it was a 10 credits course, then I handed over this course to a colleague, and now I am teaching a 5 credits course. I am also teaching other courses. For 1 year I taught solid state. Now I am also teaching a course on physics of nuclear materials.
Yes.
But concerning the quantum mechanics part, it has always been quite an introductory.
And I feel like also it's more challenging for you to have an introductory course in quantum mechanics. I feel like in the perspective of the teacher, trying to understand if the students are getting the concepts, I think is more challenging to teach in an introductory course. Because thinking about there is a course in quantum mechanics 2, for example. So the students already have the exposure, they already know the basic concepts, supposedly, and you can be more free to teach. But in introduction course, you need to be you need to think more about how you're going to introduce the concept for the first time, and you don't know the backgrounds of the students, because here in Politecnico, every semester there's more than 2,000 foreign students as well, coming from everywhere around the globe. And then it becomes more challenging as well. You need to think about the students' perspectives.
Yes, it is. I have students from many different origins and from many different curricula. And also curricula, and I would say also cultural setting. my exams are oral examinations, and it is at least half an hour of dialogue. And by this, over the years, I discovered something about maybe different ways of teaching topics in different cultural systems. I mean, from Turkey or Iran or India or South America, there are differences which are recognizable. Then I mean, there is not a fixed imprinting. I mean, not each university is equal to any other university of the same country, and not any teacher is identical to any other teacher of the same university. But yes, since the backgrounds are very different, there is almost nothing that I can take for granted. I mean, if I want to do a useful job, I have to take students to understand a certain level in order to enable them to successfully attend the following courses, like solid-state physics, which heavily rely on quantum mechanics.
Yes.
And so I must enable students to understand. Quantum mechanics is quite a conceptually complicated topic. And I mean, physicists are still debating over the deep meaning of quantum mechanics. And so it is for sure, I mean, I explain to students that whatever I am telling them is not a deduction from other knowledge they already have. I have to introduce concepts, doing my best to make them credible or to make them consistent, or at least not so much in contradiction with what they previously have.
Yes.
But I also tell them that I'm not deriving, I'm not showing in a conclusive way that things are so and so. And I underline that physics is a science of measurable quantities.
Yes.
And that statements and equations are true. We can say that they are true because they are able to predict experimental findings. And this is the basis which enables me to tell the students, these equations have already interpreted an immense variety of topics. So for sure there is at least something true. Then maybe in the future someone else will find a deeper or better way of describing the same things. But once a field has an experimental verification, that cannot be erased or cancelled.
Yes, like it would be like the Max Born interpretation of the Copenhagen interpretation. Like it's more pragmatic, and then we need to have this view because there's more philosophical interpretations of quantum mechanics that they are not. This is statistical and purely experimental. Like it predicts what the experiment does, then it's right. But of course, it doesn't tell the full story yet. And there's all of this confusion because I felt like when I was exposed for the first time, I read these interpretations and I didn't understand anything. Like in the Griffiths book last year when I read it, because Griffiths has an approach that he starts with the math. He doesn't do like in his belief, he tells in the preface of the book, he starts, let's understand how the math works, and then the end of the book I'll tell you the story. But I feel like this is a bad approach. I think the best one is like you say, like you justify what you're trying to show, because then you understand all the math. Like I understood the math and I know how the operators work and I know how to solve problems, but I didn't understand anything of the concepts involving it. And then this year I started using some other books.
Sorry.
Oh, no problem. And this year I changed this approach to like take a step back and really understand how to build and to get to that point. and then it makes sense. And I think that's the best part. Even though I was talking to the professor that it shouldn't make sense still, but it's making sense for me at least. Yeah.
Yes, you know, the word justify is a bit delicate because I really cannot truly justify.
Okay.
What I can try to do is to draw analogies. And so, I mean, one thing that left me dissatisfied the way I was taught quantum mechanics, there were some various topics, including mathematical ones, that when I ended my course, I had the impression that all these various points were specific to quantum mechanics. Later, I discovered that there are various points like standing waves, eigenvalue, eigenfunction problems, and several others, which are already fully present in classical mechanics.
Yes.
And so why leaving this wrong impression that these are some obscure, complicated points in quantum mechanics? No. There are several points, several aspects which are already fully present in classical mechanics, and then what happens is that we draw on these, we rely on these points, and perhaps we combine them in a different way. The first part of my course, I say there are two very successful paradigms in quantum mechanics, which are the point-like particle and the wave, and these are extremely successful, and quantum mechanics is realizing that none of the two by itself can give a full account, and we have to combine both. And so we rely on both paradigms, and we combine. It's like, in a sense, cooking the same ingredients in a different way. And this does not provide the full justification of quantum mechanics, but I guess, I hope, it seems a bit less strange. And so I hope this is so helpful.
It was helpful in this way, like you introduced that. I really like the way you approached the transition from the black body radiation experiment, like the analogies and stuff, like you did, like the bouquet of flowers. Like, it was very funny. And then going into for example, like showing that we cannot do a measurement with the microscope experiment that you, like the thought experiment, right? That showed the uncertainty principle, but in a better, like more didactic way, and showing that we cannot do perfectly measurement of position because we'll be disturbing the level of magnitude that quantum physics studies. We're disturbing the system by doing a measurement. So like it was this kind of ways to introduce it, like in a more classical manner, like, oh, we're throwing a photon in the particle, and of course we cannot measure the position exactly because the photon will interact with the particle, and you're going to lose the precision, like and then we can think about it in a more physical, like real world way. And then it makes more sense in the future when we see it in the actual concepts of quantum mechanics.
Yes, thought experiments are interesting, and they are useful tool used by physicists because they describe something that maybe cannot be really done, but it is a kind of a logical experiment in which one explores which are the logical consequences of concepts and theories that we already have. And so by using completely classical arguments, Heisenberg with his thought experiment, well, completely classical. The only point he added was that light is granular. It is made is not the right word, but it interacts by photon, by discrete quantities. But just on that point, and building on a whole machinery, which is completely classical, he showed that the implicit assumption in Newtonian mechanics that we can predict with high precision trajectory because we can know the initial conditions, and this is simply impossible. Impossible due to reasons which are already in classical physics.
Yes.
And so we have to cope with this, and we have to know that mathematical solutions is obviously exact, but when linking to physical reality, precision cannot be infinite.
Quantum physics requires so much in terms of not only physics knowledge, but mathematical knowledge, like probability, complex numbers, like more in more advanced levels, I believe, complex analysis in a more deeper level. Then it requires more topics in mathematically, like understanding probability density functions, and then like it's something that is more challenging because it requires so much. So like in terms of the student's perspective, what do you see as the biggest challenges that the students face when like in exams or in the understanding, and then how do you like try to help them?
Yes. I mean, as you mentioned, there are several aspects, and I mean the risk that I see more present is to focus on one aspect or another, and I would say and drowning in that specific aspect. The full meaning emerges only when keeping quite a broad view encompassing various aspects. Because reality by itself is complex. It has several facets, several aspects. And also theory includes several aspects. One might say perhaps quantum mechanics was not born before because on one side maybe there were not such an experimental evidence, but also because the various pieces and fragments which enter into quantum mechanics were not all of them were not ready. And so I mean, from my side it's quite I mean, I know that there is a difficult equilibrium because on one side I see that in front of conceptual difficulties there is a group of students who focus on the mathematical details and I mean their scope reduces to the mathematical details may be learned by heart, and I say that is not really useful because when you learn something by heart in 1 week or 2 months you lost it.
You forget.
Instead, if you understand the concept, that will remain. But some students, when I say this, I know that I must be very careful because some students, I mean, over understand this, and they tend to forget that this is physics, of science of measurable quantities, and this is not a philosophical discourse about the matter. And so some exams have a bad outcome because students express philosophical views, but they are not able to manipulate mathematics or physical reality. And so having the full view that we are talking about physics, so measurable quantities, and Galileo used to say that nature is written in mathematical terms. And this, if it is not like this, it is not physics, it is something else. But the details of mathematical derivations may hide the physical meaning.
Mm-hmm.
And establishing the link between mathematics and physical reality is a challenge. I think is maybe the most challenging part of my teaching.
Mm-hmm.
And this is what I try.
And this is a problem that generally people have. Like I was talking to a colleague in the beginning, and then I feel like he was not, I think he was from material engineering, and he didn't see very well the concept of waves. And then he perfectly understands the mathematical concept of a trigonometric function, for example, but it's difficult to understand. We use a mathematical trigonometric function because it has this periodic capacity, like it describes the unitary circle, and it's very similar to what happens in nature with a wave. That's why it's not that we derive mathematically somewhere that we got to the cosine function of cosine of kx minus omega t. We don't derive this, we just see a phenomenon, and then we use that because it behaves exactly like a wave, like with the propagation in space that varies in time, right? Like, so we need the space content and the time evolution. So it's quite hard, like people have the mathematical background, but then you need to show that the mathematics and physics is useful for modeling a system that we observe. And then creating this separation for me was quite hard when I was learning as well.
Yes, this modeling word you use is a crucial one.
Mm-hmm.
I mean, mathematics is a construction of our mind.
Yes.
And some mathematicians say that mathematics is not a science because it is not in contact with reality.
Mm-hmm.
And the surprising thing, in a sense, is that our construction of our mind resonates with reality. I mean, is able to interpret and understand physical reality.
Mm-hmm.
And we always, I mean, when we build theories, and we always must keep in mind that this is something we are building, which has, it is useful if it has point of contact with reality, and probably it is far from fully penetrating the meaning of physical reality.
Mm-hmm.
Now, in the history of physics, there are different approaches. The most extreme one says that reality is what we measure. Mm-hmm. I mean, there was a book on which I studied on electrical circuits.
Yes.
This was surprising because it was a full book on electrical circuits. Mm-hmm. In which the word electron did not appear. Because the author was very operational, and at the beginning he defined what is voltage. Voltage is what we measure by voltmeter. Mm-hmm. And what is current? Current is what we measure with an amperometer.
Yes, I had the same experience because I used the book for electrical engineering, and it's way more focused in solving circuits. So it's linear algebra, pure linear algebra. You don't even see physics most of the time.
This is quite an extreme view.
Uh-huh.
And there is one point which is worth keeping of it. I do not share this view. Mm-hmm. But there is a point which must be kept, and is that our mind construction does not exhaust all the aspects of reality.
That's true.
It has points of contact. It allows to understand very important aspects, but reality, I mean, in a sense, escapes our closing them. Mm-hmm. It's more, yes. Which also means that there is always something more to discover.
Mm-hmm. For sure. Well, there's another topic that I would like to discuss very briefly to end our conversation. Which first is the examinations in Italy. Here I'm facing a different perspective because most of my courses have oral exams in which we need to discuss with the professor and show them what we've learned in the entire semester, basically, right? And then, yeah, that's completely different from the experience in Brazil and I believe in other countries, which we do a lot of written tests, like tests throughout the semester, like generally 3 tests, and then like maybe you have a final exam. And the oral exam is a completely different approach, like maybe adds more pressure. It's a final exam and you're discussing with the professor. So I would like you to talk about, like, was it always like that in Italy, or it's something that started recently?
Historically, it was much more like that.
Mm-hmm.
Then, since several years, due to the increased number of students, basically,
Okay.
more and more exams become written tests, because managing large numbers,
Mm-hmm.
I mean, just by oral exams is very time consuming.
Okay.
And
True.
so it is more practical, faster to move towards a written exam. And there is one aspect of written test that I miss in oral exams,
Mhm.
is that in written test you have to manipulate and perform
Yes.
computations, and in an oral exam you cannot ask to really solve a problem.
Mm-hmm.
Also because in a written test you must have a time to try one way, say no, this does not
Mhm.
lead
Yes.
nowhere, and let me try in a different way.
Mm-hmm.
And in an oral exam one cannot expect that the student immediately finds the best way.
Yes.
And so this is something that the oral exam misses.
Mm-hmm.
On the other hand, I recollect what I was saying a moment ago.
Mm-hmm.
In an oral exam, one understands much more if a student has different pieces of knowledge
Mm-hmm.
separate from each other, or he managed to have kind of an overall view, which must be, in a sense, his own.
Okay.
Because we as teachers, we present several topics, and in a sense, I mean, exaggerating a bit.
Mm-hmm.
Real knowledge is the connections about the topics, and studying the different aspects,
Mm-hmm.
each student has to, I mean, we try to explain which are the connections,
Yes.
but each student somehow has to find his own way of connecting things.
Mm-hmm.
And this is tested in an oral exams and cannot be tested really in a written test.
Yes.
And
Because also it's hard to spot the mistakes, because in a written test either you know how to do it, or if you don't know how to do it, like you maybe try to develop a little bit, but it's hard to find exactly what the student missed. I feel like maybe in the oral exams it is
yes, I mean,
easier.
an oral exam is interactive. I mean, it's
Yeah.
not like you ask a question and then I am silent and wait
Mhm.
for the development. It is quite interactive. And this allows, I mean, there are cases in which the student is not able to develop a full or complete answer.
Mm-hmm.
But I mean, I ask him to reason about it, and in a sense we are reasoning together.
Mhm.
And sometimes the student has the impression he does not know the answer, and then he begins to reason about it, and several elements come out
Uh-huh.
which are perhaps not the full and complete picture, but are important elements of the picture. And so, in evaluating the exam, yes, I cannot say he has the full clear picture, but he has several elements, and he's able to reason about it, and this is obviously evaluated.
Yes. So for the last topic, we will discuss a little bit about applications of quantum mechanics. This year, it's the 100-year anniversary of quantum mechanics with the paper like the Schrödinger equation published in 1925, and also the Nobel Prize this year was related to quantum physics. And then, like, how do you describe like the applications of quantum physics, the relevance of it? Because people generally, like, when you see people talking about quantum physics, they say, oh, they're crazy. Like the people there are, the normal people in society, they're not aware of the relevance that we have for quantum physics makes correct predictions. And then we see like the Nobel Prize this year, it's on quantum physics, and like what is the relevance of the course like for the life of the professionals who learn about this?
Yes. Well, I would say yes, quantum physics is crucial to describing the behavior of matter at an atomic level. And I mean, there are an immense variety of physical phenomena which are exploited in technological applications, which can be understood and lead to applications only because they are understood by quantum mechanics. I mean, just that's the most relevant. Semiconductors. Semiconductors have changed our way of life. I mean, if I think back of how life worked 50 years ago, this is very, very relevant differences. And this has been possible because of the understanding of the behavior of semiconductor at an atomic and the crystal level. The peculiarity of the Nobel Prize you mentioned is that, I mean, we always say quantum mechanics describes the matter at an atomic level, but there are cases in which so many atoms or so many electrons, in the case of, in particular, Josephson junction, so many atoms or so many electrons behave in the same quantum mechanical way that also the macroscopic behavior behaves in a quantum mechanical way, which was not foreseen till a few decades ago. But there are some, I mean, it is a bit a loose analogy, but there is some analogy. Laser light is basically something that does not occur in nature.
Yes.
There are, at the astrophysical level, there are masers, microwave, there are something like this, something like that. And what is in the essence laser light, let me say in a loose way, light is made by photons, and it is a way of convincing photons of doing exactly the same thing. And so the whole beam of light does things which does not do if each photon behaves its own way, so to speak. And the same for, I mean, superconductivity by itself is a way, I mean, electrons combine in such a way that billions or maybe even more of electrons are exactly in the same quantum state, so they perform exactly the same thing. And Josephson junction, for which the Nobel Prize, I mean not the junction which was already known, but the fact that in Josephson junction some quantum mechanical behavior is measurable at a macroscopic level is based essentially on the same thing, that single electrons behave in a quantum mechanical way, but if billions of electrons behave in the same quantum mechanical way, that the peculiarities of quantum mechanical behavior become measurable even at a macroscopic level. Then it is not so trivial because, I mean, these experiments were done at temperature very close to absolute zero, a few millikelvin, so it is not everyday experience. But it was a macroscopic measurement.
So well, that's it. I already took too much time of Professor Beghi's. he actually has to go to another city now. So thank you very much, Professor, for giving your time, and I hope you have a great day. You're helping the students to learn and try to understand these concepts, and I think it's very good to inspire like our generations, the next generations, to of course keep going with physics. And yeah, thank you very much.
Thank you for inviting me. And you know, it's it is not. I mean, it is true that. I mean, teaching is interesting because explaining things is also a way for me to understanding them better.
Yes.
And interaction with the students has always been crucial. I mean, some major steps in my understanding of physics came from questions from students, and so this is interesting for me also.
Awesome.
So thank you.
Thank you, Professor.